Hey everyone, in today's Chem Help video we're going to look at a basic titration calculation. Titrations are a really important part of our course. They come up in the WACE exam all the time. They vary in complexity from very easy to a bit more tricky. So I'm just going to go through the basics of a simple calculation today and just to show you how to go step by step through them. Alright, so let's have a look. Alright, so how to do a titration question. Now, whether or not we're doing an easy one or a hard one, they all have the basic structure that's very similar. So if you can follow the steps, you can just apply it to different situations, different reagents, etc. Alright, so here's an example for you. So we've got a sample and we're given a mass of an impure substance. Now, of an impure substance, of course, we can't calculate moles because it's impure. We want to find the percentage purity of that substance. And to do that, we need the mass of the pure substance. And we know that the pure substance that we're after is sodium hydroxide. But this sample's got other stuff in it. So we can't use that mass, but that's important at the end. And we take that sample, we dissolve it in distilled water, and we're hoping that the sodium hydroxide would form dissociate into its ions, and we make it up to the mark in a 250 ml volumetric flask. So we know precisely the volume. That's what the volumetric flask is for. To that, we're going to titrate 18.5 mils of a 0.2 mol per litre standardised solution of hydrochloric acid. So that would have been standardised against a primary standard. And we found that it was required to react with 20 ml aliquots. Now remember, an aliquot is a sample taken with a pipette from the 250 ml volumetric flask. So the volumetric flask, we know the volume precisely, and the 20 ml aliquot, we know the volume precisely. From the burette, we know the volume and the concentration that came out. And because we know the volume and the concentration precisely, we can calculate the number of moles. From that, we need to go through the calculation steps and determine the percentage purity of our sample. So what are we going to find out? We're going to try and calculate the number of moles of hydrogen ions that reacted. That's what came out of the burette. From the number of moles of hydrogen ions, we then calculate the number of moles of hydroxide in that aliquot. So that came from the pipette. The pipette went into the volumetric flask and changed colour, or the indicator changed colour, when you reached endpoint / equivalence point. Hopefully those two are very close together. From that, we step it up from the 20 ml aliquot into the 250 ml volumetric flask. From that, we can determine the number of moles, or the mass rather, of the sodium hydroxide, the pure sodium hydroxide. And then we can work out the percentage purity of our sample, which we were given a mass for at the very beginning. Okay, so step one of these really should be to draw a diagram. It helps organise our thoughts. So you can see there that we've got a sample dissolved in 250 ml volumetric flask. A 20 ml pipette takes an aliquot of that into another volumetric flask. We then take that, hydrogen ions come out of our burette, we swirl it so we get endpoint and change the indicator colour. Now, choice of the right indicator is an important thing, but we'll cover that in another video. So step two is to determine the number of moles of substance that actually came out of the burette. This is a standard step. If you do nothing else, find the number of moles, you'll get 1 mark for this, and you should be able to do that straight away because you'll always be given the concentration and the volume. Okay, so determine the number of moles of H plus that actually reacted. So N equals C times V. Make sure your volume is converted from mils to litres. That's a mistake a lot of people make because it's just a simple oversight. Okay, so 0.200 mol per litre solution times 0.0185. That's the 18.5 mils turned into litres. And that's how many moles of hydrogen ions actually reacted. So there's our first step of the calculation, second step in our process. Now, what's in the conical flask? That's the one that aliquot went into, not the volumetric flask, but the thing we did the titration in. Alright, so we use the equation to determine the number of moles of hydroxide which reacted with hydrogen ions. That's in the 20 ml sample. Now, in a neutralization equation, it's usually a 1-to-1 ratio. Okay, so you've got to look at your substance. So you've got to have an equation somewhere. In this case, it's pretty easy. HCl plus NaOH makes NaCl plus H2O. So it's all 1-to-1 to 1-to-1. Alright, so you need to look at the different base or acid that you're going to use. That's quite important. But in this case, it's 1-to-1. And that's and it's good to annotate that with all subscript in the 20 ml so they keep track of everything. So that's 1 times 3.7 times 10 to the minus 3. There's the number of moles of sodium hydroxide that were in the conical flask. They actually reacted. Okay. Now we want to find out how many moles are in the volumetric flask. So this is the stepping up step. Okay. So we know the number of moles of hydroxide in the 20 ml sample, and we want to know the number of moles in the 250 ml sample. we can use the concentration for this. So concentration is number of moles on volume. So you've got the number of moles from the previous question, you divide by the volume, gives you then concentration. So we have the concentration. Now the concentration won't change. When you take a sample from the big bottle, the volumetric flask, to your aliquot, the concentration is the same. You're just taking a smaller piece of it. So it's the number of particles per unit area stays identical. Right? The moles are quite different, of course. All right. So then what we do is we then take that and we work it out in 250 mils. So we know our concentration, we know our new volume. We then step it up, and we get 4.62 times 10 to the minus 2, and if you've done it right, you should get a bigger number, of course, because you've got a bigger amount. So that's that one. A more efficient method is using this method. We combine the steps. Now, whether you like stepping it out as 2 steps or combining it as 1 is completely up to you. It's a personal preference thing. I like combining it because that way it's easier for me, but you might find it easier or more logical for you to step it out. What you've got to remember is that C1 equals C2, or the concentration in the 250 equals the concentration of the 20. So that's the same. N1 on V1, which is concentration, equals N2 on V2, which is concentration. But now our volumes are different and our moles are different, and we just swap it around. So it's the number of moles in the new, or the bigger sample, is 250 on 20 times the number of moles in 20. Every time you do this, it's going to be the larger volume divided by the smaller volume times by the number of moles in aliquot. Now what some people get tricked with is that they practice these questions and it's always 250 over 20, 250 over 20, and then someone gives you a 500 over 20 or 500 over 25 or a 250 over 25. So make sure you read the question about what is the aliquot size, but it's always bigger over the small. Calculate times by our number of moles and same answer. So you can combine it if you like, or you can separate it out. We now have the number of moles in the 250 ml sample. So now what we need is the mass, and that's pretty straightforward. So we know our moles, we want our mass, so it's a simple, the number of moles of OH is equal to the number of moles of NaOH. Now make sure you say that mole relationship. We're actually calculating the number of moles and therefore the mass of sodium hydroxide, not the mass of hydroxide. It's sodium hydroxide. That mole relationship, it's pretty important that you say that, and you can lose a mark in a previous waste paper if you didn't do that step. So showing that's quite crucial. Then we can use good old N equals little m on big M, or rearranged M is N times M. Calculate your molecular mass carefully. There's another mistake people often make. And we get our value of 1.85 grams. That's how much sodium hydroxide we actually have. Remember, our pure sample is going to be smaller than our impure sample, so that's right. Now what we do is we determine the percentage purity by simply getting the mass of the pure over the mass of the sample times 100, so 1.85 grams over our 2.34 grams, which is our impure amount, times 100, 79.2%. So by doing those 6 steps, so 5 calculation steps and 1 diagram, you're very easily able to do a titration question. If you follow that procedure, you'll get it right every time, and makes life a lot easier for you. So hopefully that's helped. Make sure you practice a few of these. Give them a go. Try them in different situations, but you'll find the structure remains the same. It's a lot like an empirical formula question. They don't differ that much in terms of structure. It's just the numbers that change. So good luck, and we'll see you at the next one.